Hello, class. This is Mr. Hart, and in this podcast, I want to start the gravity and orbits unit. But before we do that, we need to go over a term called centripetal force. Okay, and if you think about it so far, everything we've done in physics has been a linear movement, right? In the forces chapter, we've been, drawing these lines, either left or right, up or down, okay, along these flat surfaces of where things are moving. But we haven't thought of any type of rotation, okay? Things that are moving about themselves. Now, fortunately, we've talked about center of mass, and a lot of things do rotate about their center of mass, which is nice. Okay, but we still want to think about the terms of the rotation. Okay, and in popular culture and movies, you may have heard of something called centrifugal force. But I want to ask the question: is that really a force? Okay, if you think about it, this is a scenario a lot of people give. Is like think about those spinning rides at, theme parks or like the teacup ride. Okay. Again, I apologize for my bad writing because I'm using a touchpad, but imagine you're on a circular ride and it's spinning you around. Okay. You're on the outer edge. Okay. All the people are on the outer edge. Okay. And when it's spinning really fast, if you think of this, force pushing us towards the outer edge, right, which holds us against the wall, it kind of pins us. Okay, as this goes around and around in a circle, right? Okay, it spins around, and we can feel that force against the wall. And so people have kind of termed this idea of, moving against the wall as centrifugal force. And so they would label this is centrifugal force. Okay, this pushing against the wall. But is this really what's happening? Are we being pushed against the wall? Okay, some people might think we are because that's how it feels. But we actually are not being pushed at all. The wall is kind of pushing in on us. So if you think about a rotation, okay, any type of rotation, we have two things that are happening, okay? We are moving in the direction of the rotation, right? So if I was sitting at this point and the ride spinning around in a circle like this, I am moving this direction, right? I'm moving in the direction of this arrow, right? This velocity arrow is the direction I'm going. But we also feel that force pushing in on our wall. We're being accelerated towards the center, okay? And so the result is the velocity and the acceleration are always perpendicular, okay, like this shows. But we get this kind of effect because we want to move in this direction, right? We want to move to the left. Okay, like this shows, but we're being kind of shoved downward. Okay, and so our inertia is taking us this way, but the wall is pushing us this way, and so we feel a force kind of pushing on this direction. But then it'll move us, right? Let's say we end up at this point. Now we want to go this direction, but the wall's pushing us in this direction. Our acceleration or the force is going in this way, so it will move us that direction. Then we're at this point. We want to go this direction, and the wall is going to push us in this way, and so on and so forth. So no matter where we're at on the ride, our acceleration's towards the center, and our velocity is towards the outside, so we get this nice consistent motion along the outside. And so again, the centrifugal force is not real. It's just this effect that comes from us wanting to move one direction and the wall pushing us to go another, okay? So that gives us not centrifugal force, but centripetal force, okay? So centripetal force, the P version, right? P-E-T-A-L, and centrifugal force, okay? Make sure you understand the difference between those two. Centripetal force is real, and centripetal acceleration is real. Centrifugal force is not. Okay, so centrifugal force is fictitious, not real. It's what we think is happening where it pushes us along the outside. What's really happening is centripetal force, this motion towards the inside of the rotation. Okay? All right. And so here's one of your vocabulary words. It says the centripetal acceleration is the change of direction around the center caused by the centripetal force. So again, think about that diagram. As you're moving around, you're always accelerating or changing direction towards the center. And that total effect is what makes us feel like we're moving towards the outside. Okay? Okay, so now we can actually calculate it. And this is the equation we're using. The centripetal force is equal to the mass of the object times the velocity of the object squared over the radius of the rotation. Okay? And if you think about it, this makes sense, right? The more mass of the object, the more force that's going to be needed, right? The faster you're going, the more force you're going to need to change the direction. The larger the disk, the slower the rotation is, so you don't need as much force, right? So if you think about the terms, this makes sense, okay? And so the centripetal force is the mass times the velocity squared over the distance of the rotation, okay? So let's try an example problem, okay? A 40-kilogram child is on a merry-go-round that has a radius of 1.5 meters and a velocity of 5 meters per second. What is the centripetal force on the child? Okay, so here's the merry-go-round. The child's holding on. He weighs 40 kilograms. He has a force pushing in on him, or he's holding on, right, with a certain amount of force. So we want to calculate this force right here, okay? How strongly is he holding on, okay? And so we know the mass of the child. Oops. Okay, so we know the mass of the child. We know that's equal to 40 kilograms. We know the radius, okay? It's 1.5 meters. And we know the velocity, right? It's 5 meters per second squared. Or sorry, 5 meters per second. And so we're just going to plug it in to this equation. Centripetal force equals mv over r. mv squared over r. Okay? So we get 40 times 5 squared over 1.5. Okay? So that's going to give us 40 times 25, okay, which I believe is 1,000 if I'm correct. And we take that and divide by 1.5. Hold on, let me double check with the calculator. All right, so 40 times 25 divided by 1.5 equals 666, okay, newtons. Okay, our unit's going to be newtons. Okay, and so we just take this mass times the velocity squared over r. Okay, simple equation. That's how we can calculate the centripetal force. Okay. All right, let's try one more problem. So if you're doing this podcast for participation, let's try to answer this question. So a 50-gram fly, that's a pretty big fly, is on the edge of a CD that has a radius of 30 millimeters and a velocity of 2 meters per second. What is the centripetal force on the fly? Okay, so again, we have this CD, it's spinning around. We have a fly on the edge. Okay, he has a certain mass. Okay, he has a certain velocity, and he has a certain radius. Okay, but we have something we need to work out because it says 50-gram fly, but grams is not our SI unit, so we need to convert it into SI, which is kilograms. Okay, so we're going to get 0.05 kilograms. Okay, then we put in 2 meters per second, 2 meters per second for the velocity, and then the radius is 30 millimeters. Same thing here. We don't use millimeters, we use meters, so we need to convert that. So that's going to be 0.03 meters. Okay, so now we have M, we have V, we have R. We just plug it in. So we have FC, or centripetal force, equals 0.05 times 2 squared over 0.03. Okay, and so when we plug that in on our calculator, we get 6.67, again, newtons is our unit. Okay, so 6.67 newtons. Okay, all right, so again, sorry I'm being a little slow on the calculations, but hopefully that makes sense. Hopefully you understand the difference between centrifugal force and centripetal force. Okay, centrifugal force is not real. Centripetal force is real. Okay, and we can calculate it using the equation Fc equals mv squared over r. Okay, so you may be wondering, what does this have to do with gravity and orbits? But we will get into that next time. Okay, and you'll start to see why it's important that we have the centripetal force equation before we get into gravity and we get into orbits. Okay, but let me know if you have any questions, and thank you for watching.